Let us design a reduction rule. So now using this we can design a reduction rule, right? So we are saying there is always a minimum vertex cover that picks all of V1 and nothing from V0. And so what we can do, what could be a reduction rule? We know there is always a solution that picks all the vertices of V1. Yes. So let's see. So we can design a reduction rule in the following way. So we solved this LP of this, we got these values. Based on these values, we formed these sets V1 and V half. The reduction rule says that you can, if given this instance, you can create an equivalent instance by throwing away V1, basically taking all of V1 in the solution, right? Note that when you delete V1 from the solution, V0 becomes isolated vertices, because V0 had neighbors only inside V1. So you could actually even throw away V0 also, right? And I'll not prove the safeness of it because, I mean, we all have seen, I mean, if we know that something goes to the solution, then for vertex cover, we know that we can safely delete it, right? So this is a safe rule. Now I applied this rule. Now what remains in the graph? V half. So now we know that, let's call this graph G prime and this graph K prime, right? I want to prove that, I want to get a kernel for this, so I want to prove that this graph has small size. And I know that the vertex cover of this graph is exactly equal to V half. Okay. Now, here let's do this. So here again, let's go back to this LP. When we solve this LP, okay, suppose this LP value turned out to be greater than K. So in the very first place, even before doing it, when we solve this LP, we got these AV values, and I'm saying, so when we solve this LP, suppose it was the case that summation of AVs was greater than K. Then can such a graph have a vertex cover of size at most K? Because we know that if AV is an optimum solution, if it's an optimal solution to LP, then its size can be at most the size of any minimum vertex cover of G, right? So if its size alone is strictly greater than K, then you can't have a minimum vertex, then you can't have a vertex cover of size at most K, right? So in the very first place, even without doing this, when you solve this LP and got these values, you first check whether this condition holds. If this holds, you can return a trivial no kernel, right? Otherwise, we are in the case when this thing is at most K, right? So we can always assume we are in this case. Now let's come back to this. We have reduced our graph where we only have V half vertices, right? Now then how many vertices can there be in V half if this is the case? I mean, can there be more than 2k vertices in V half? Note that, what was the set V half? They were all the vertices which got value equal to half. And I know sum of AV values is at most half. So what is the size of V half set? If the size of V half set is supposed strictly greater than 2k, then when you sum up the AV values of these greater than 2k vertices, will they add up to at most k? No, right? So basically, the size of V half is at most 2k, because if it was more, then when you sum up the AV values of these vertices, it cannot be less than half, right? And this is exactly because all the vertices are this is because every vertex has value equal to half. If suppose some vertices had value strictly less than half, then I don't know. There could be many vertices, right? So because of this, the size of V half is 2k, and this is how we get a 2k kernel for vertex cover. Okay. So what we did basically was we solved LP. We based on the values that the vertices get, we like we partitioned them into 3 parts, V0, V1, V half, and we proved that there is always a solution that takes whole of V1 and doesn't take anything from V0. Moreover, we observed that V0 was an independent set, like V0 had neighbors only inside V1 and it was an independent set. So we throw away V1, when we throw away V1, V0 becomes isolated, so we throw away V0 also. So what is left is V half, right? And we know that when we would have solved the LP, if the LP solution was more than K, we would have said no, then graph can't have a vertex cover. Otherwise, the LP solution is at most K. If the LP solution is at most K, the size of V half cannot be more than 2K. So when I've thrown away V0 and V1, V half size is at most 2K. This is how we get a kernel. Yeah. Okay, so this is because of this. If you give me any optimum solution to the vertex cover LP, then this sum can never be more than the minimum vertex cover of the graph. And this is easy to see. Think about it. Why? Look at the minimum vertex cover of the graph. Okay. So let's do this. Whatever vertices you pick in the minimum vertex cover of the graph, let us give the corresponding variables value 1 and let us give 0 to all the other variables. Is this a feasible solution to this LP? Right? So this is a feasible solution to this LP. So, and what is its value? Its value is exactly equal to the size of the vertex cover. So the vertex cover, this is a, yeah. Right? So this is clear, the kernel is clear. Okay, so maybe I'll briefly talk about what I promised. So I said that you can definitely do this, and for this you need to solve this LP, and of course there are algorithms that solve this LP in polynomial time. There are general algorithms, but they run in bad polynomial times. And so I said that for this LP we'll see a nice polynomial time algorithm that solves this LP okay. And basically, how do we do it? We reduce the problem of solving this LP to the problem of finding a vertex cover in an appropriate bipartite graph. That's it. And you know that a vertex cover in an appropriate bipartite graph can be found in how much time? Poly, but do you know what is the exact polynomial time? Have you seen Hopcroft as an algorithm? No. So you saw the algorithm for bipartite matching in bipartite graphs using network flows, right? So that's one. So how much time does that take? Maximum flow times n plus m, right? So it's like some cubic time, not more than that, right? So cubic time, but I don't know. There is also an algorithm to find matching in a matching or a vertex cover in a bipartite graph. They're both the same. We know that by Koenig's theorem, which runs in time m root n. Okay, but that's okay. N square is good enough for us. So let's just at least see an overview of. Let me just quickly try to give you an overview of what it is. So we want to solve this LP, the vertex cover LP. See, for that what we do is, we are given this graph G, we try to construct an appropriate graph an appropriate bipartite graph. And when I say appropriate bipartite graph, I mean try to basically try to encode what the information that we actually need from the graph G to solve that LP into a bipartite graph, that sort of a thing. We'll see what that information is, and again we'll see what that information is. It will only be clear why we are why we are constructing such a graph only when we see the proof. Okay, so let me just give you a proof. So the goal is clear, right? You're given a graph G, you write an LP of G, and now you want to compute an optimum solution to this LP. Compute an optimal solution to this LP. Okay, and to do this I'm saying, and now I'm giving you an algorithm to compute an optimal solution to this LP. Okay, for this the first step is I'll construct a bipartite graph, and I'll tell you what that bipartite graph is. I'll call that bipartite graph H. Okay. So what is H? So the vertices of H are basically, look at the vertices of G and make 2 copies of them. Okay. So let's say the vertices of G were U1, U2 to UN, or say, yeah, U1, U2 to UN. Then I make 2 copies of these vertices, or yeah. Then I make 2 copies of it. Let's say I make V1 copy and W1 copy. Okay. So basically it's like I have made 2 copies for each vertex. Okay. And how do I put an edge between this bipartite graph? Suppose there was an edge between U1 and U2 in the graph EG, then what I do is I look at I put an edge between both the copies, like what are the copies of U1, V1 and W1, and what are the copies of U2, V2 and W2. So I put an edge between 1 and 2 like this and 1 and 2 like this. Okay. This is the construction of the bipartite graph. This is the bipartite graph that we will be working with. Okay. And now the algorithm is very clear. The algorithm is very simple. What we do is we find a minimum vertex cover of H. Okay. This can be done in polynomial time. Let's say this is S. Based on S, I give an assignment to the variables of this LP. Okay. Sorry? Yeah, so I'm saying first step is constructed this graph. The construction is clear, right? The second step is I computed a minimum vertex cover of this graph and I'm calling that graph S. Third step is based on S, we will give an assignment variables of this LP of G, okay, of the graph G, this LP that we had here. So that's a third step, and then of course we'll prove that this assignment that I've given is feasible, and then we have to prove that it's not just feasible, it's the minimum possible, like it is an optimal assignment. Okay, but first let me give you an assignment. The assignment is as follows. So for any vertex ui in G, what is the assignment? I'll give it 1 if I look at, now I'm giving this assignment based on the vertex cover. If suppose S picks both the copies of ui, like look at the vertex cover S, it is picking some vertices of H, right? And vertices of H correspond to vertices of G, right? For every vertex in G, I have 2 copies of that vertex. So I look at S and I look at all the vertices of G for which S has picked both its copies. For those vertices, I give them value 1. Look at all the vertices for which S has picked exactly 1 copy. For those vertices, I'll give it value half, and the other vertices for which S has picked no copy, I'll give them value 0. That's my assignment. So 1 if S intersection, so ui copies were vi and wi. If S was picking both of them, then I give this vertex value 1. If the same thing was picking exactly one of them, no matter what, I was giving it value half, and I was giving it 0 if it was picking nothing. Right? The assignment is clear, the construction. Okay. Let's see first. So the first, now I'll prove that this is a feasible, and I want to prove that this is an optimal assignment. For that, I'll first prove that this is in fact feasible. That means it satisfies all the LP constraints. So prove that this XUI assignment is feasible. Why is it feasible? Can someone quickly say? So to prove feasible, what we have to say, suppose there are 2 vertices ui vj in there is an edge here. So for that we have to say that then xui plus xuj is greater than or equal to 1. Okay. So look at any edge in the graph. For that edge we created 2 edges in H. Right? If uj was an edge, then I would have had an edge in vi Wj and Vj Wi, right? I would have these two edges corresponding to this. Now S is the vertex cover for this graph. Out of these 4 vertices here, S will be picking at least 2 of them, right? I don't know which 2, but some 2, right? Now look at all the cases. If suppose S pick both of these vertices, right? Then okay, or in fact, if suppose S picks both these vertices, both 1 vertices, then that means S was picking Ui, like S was taking both the copies of Ui, in which case X of Ui would be 1. So this would hold. If otherwise, and the same holds, if S was picking both these copies, then also for Uj, it was picking both, so Uj would be 1. Otherwise, S was picking 1 this and 1 this. It was picking exactly 1 copy of Ui and exactly 1 copy of Uj, in which case it would be half for both the things, and this would still be at least 1. Make sense? So this is definitely a feasible assignment. So now I have to prove that it is an optimal assignment, right? So again, the way so this is the last step. So it's not very difficult. So the way we'll prove it is the following. So we'll say that, okay, look at any optimum solution. So let's say, let this be an optimum solution to the LP, like this is some optimal solution. If I prove that whatever I have constructed here, its value is at most this value, then are we done? So U of Vi was some optimal solution. I don't know what it was some optimal solution, and if I prove that the value that I have computed is at most the value of that optimal solution, what does that mean? So this value was the minimum possible, then of course this value is also minimum possible, right? Like, in fact, if I can prove that, then, and if this was actually minimum possible, this will hold with equality. Okay. Now how do I show this? For showing this, we have to, like, there's just a couple of simple things that we observe. So as she pointed out, if we look at any optimal solution to the LP, its value is at most the vertex cover of the graph, right? Okay. Forget optimal, suppose I give you any feasible solution to the LP. Is there a relation between any feasible solution to the LP and a maximum matching in the graph? So what I'm saying is, suppose this was a feasible solution to the LP. Just feasible, I'm not saying optimal, okay? Of course, it will hold for optimal also, because any optimal solution is feasible. But in fact, if it was any feasible solution, then what can I say about this value with respect to the maximum matching in the graph? Okay, tell me if this is true. Mm of G is the maximum matching in the graph. Can this value be less than the maximum matching in the graph? Again, what is the maximum matching? It's a collection of edges. And because it's a feasible solution, it has to satisfy the constraint that for every edge, both its endpoints should add up to at least 1, right? And a matching is a collection of disjoint edges. So if you look at the vertices corresponding to these matching edges, and if you add up their values, its size, like this size will be at least the size of the maximum matching, right? The number of edges that you have, because for each such edge contributes at least 1 to this sum disjointly, right? So this is true. And now how are we going to use this? This is true. So this is true for any graph, right? In particular, this is true for the graph H also that I have constructed, bipartite graph. And bipartite graph has a nice property that maximum matching size is actually equal to the vertex cover of H, which is nothing but the size of S. right? So there is a relation between a feasible solution of H and the vertex cover of H, right? And now observe that there is also a relation between S and the not just the feasible solution, the solution that we have constructed, the XUI solution. Can you see a relation between the size of the, can you see a relation between this is the thing that we have constructed, okay, for G. Can you see a relation between this and the size of S? Because for example, for each vertex that you in S, this value you can associate a half value to this. For example, here UI gets value 1. UI gets value 1 because there were 2 vertices in S there. And if for all the other vertices whose only one copy was picked, there is a value half here, right? So this is indeed true. So what we have actually done is, there is a relation between a feasible solution of H and the maximum matching of H. Because it's a bipartite graph, maximum matching of H is equal to the vertex cover of the graph. Vertex of the cover of the graph is S, and the way we have computed our assignment, there is a relation between S and the assignment. And what is the relation? This is equal to twice, right? So let's see what we have. I'll just write this thing, and we are just one step away from the proof. So what we have is 2XUI. So this is XUI is the assignment that we have proposed, okay, for which we want to prove certain thing. We have, what we have is that this is at most, right? This is at most let me just say y of v for every vertex v in VH. Like basically it is summation over all VIs and WIs, right? Because it's basically, this is the feasible assignment for this set VH. So you have to take the assignment corresponding to every vertex. So for basically every vertex in VH, where this is any feasible solution to the LP of H. This is what we have. Now, what did we want? So we wanted to prove this. Now this y is different. Okay, we wanted to prove that whatever we have computed, its value is at most any optimal solution to G. That's what we want to prove that this is the optimal possible. So basically, if we can relate a feasible solution of H to an optimal solution to G, we'll be done. Like that's the kind of thing that we have to look for. Now, to do so, observe this. So to do so, I want to give some feasible solution to H based on some solution on G. Okay. Okay. So what I'm saying is the following. So okay, this is really the last step. I mean, I hope you're not getting confused. So, okay, suppose I give you some assignment, some feasible assignment for the LP of G, okay, the linear program for G. From that, can you give me a feasible assignment for H? Where is it? For H, for this bipartite graph. Okay, so let me just tell you this, and then let's see if we can prove it. So there is a feasible assignment for G, okay. So G as in, so for every vertex in G, you have given it some value. Let's say, if look at a vertex UI, whatever value you have given to that vertex in G, give the same value to both its copies in H, the same value. And then is this a feasible solution for H? To prove that it's a feasible solution for H, we have to say that for every edge something holds, right? So look at any edge in H, right? So look at this edge. So what is this edge? This is an edge between some Vi and some Vj, What is Vi? Vi corresponds to some Ui and Vj corresponds to some Uj. What was the value that I gave to Vi? The same value as Ui. And what is the value that I gave to Wj? The same value as Uj. And why is there an edge between them in H? Because there was an edge between Ui and Uj in G. So, because there was an edge in G between these two vertices, their sum will add up to 1, and to these vertices I have given them exactly the same values as Ui and Uj. So, their sum should also add up to 1, right? Right? So, given any feasible assignment to G, you can always give a feasible assignment for H. Okay? And now, what is the relation between their sizes, or by sizes as in, let's say, suppose Z was a feasible assignment for G. Using Z, we constructed another assignment, like we constructed an assignment for H this way, like look at for every vertex, like we give the same assignment to both the copies of H as they were getting in G. This is how we got it. So, is there a relation between these values and these W values? Okay, is there a relation is what I am asking. So, basically what is happening? See, these vertices will get the same assignment as their copies. Every vertex has 2 copies, right? So, whatever is this sum, like it will be what? What is this is twice as this, right? Because there are 2 copies of every vertex there. So, this is what we have. So, now what have we done? We have a relation between a feasible assignment for G and a relation between a feasible assignment in H, right? And we had a relation between a feasible assignment of H and the assignment that we had constructed, right? So now the proof is as follows. Consider any optimum assignment for G. Based on that optimum assignment, I can give a feasible assignment to H this way, that give this same assignment to both the copies. I can always give a feasible assignment to G. And what do I know? I know that if Z, okay, yeah. So suppose, and I know that the assignment that I have given to H is twice the assignment that you started with, right? And I have started with an optimal assignment for G. I could have started with any assignment, but I am starting with an optimal assignment because I want my proof to work. Okay. So, I know that there is always a feasible assignment for H whose size is twice the optimal assignment, right? And I also know that whatever I have constructed is at most the feasible assignment for H. So, combining both these things, like I can write it like this, right? So again, you start with some optimal assignment for G, okay? Using this optimal assignment, you constructed a feasible assignment for H. And this is the relation between them, their sizes. Now this is a feasible assignment for H. How did we get this? If this is a feasible assignment for H, we know its size has to be at least the maximum matching of H, right? And we know because it's a bipartite graph, this maximum matching is equal to the vertex cover size, which is S. And we know that whatever I have computed has this relation with S. So combining all this chain of equalities, what we get is that twice of xui is what we had constructed, is equal to twice of zui, and ui was an optimum solution for G. So what we have, so 2 gets cancelled. So what we have actually constructed has size at most any optimum solution of G. So what we have actually constructed is indeed an optimal solution. Again, the crux lies in this chain of equalities. You start with an optimal solution of G, you get a feasible solution of H, which has a nice size, like the size dependency is nice. The feasible solution of H has a relation to its maximum matching, which has a relation to the vertex cover of the graph, vertex cover of H, and the way we have assigned our assignment, it has a relation to the vertex cover of H. So this relates an optimal solution with whatever we have computed.